Welcome to Spring LIB.
Alrighty, so we got a particle at the origin of a coordinate system. There's our origin, particle sitting down here. And there's some initial conditions that we know. We know the initial velocity of the particle. Put that up here. It's a v naught equal to 5 meters per second. And it's in the x direction. So there's an I hat unit vector here. This is the x direction, and this is the y direction. All right. So the initial velocity vector sketched out would be right here. We also know that there's an acceleration that is going to be acting on the particle during the whole time it's in any motion at all. So we will go ahead and leave that here as well. Acceleration. This guy has a vector as well. And the acceleration is equal to 6 square root of t. And that, though, is going in the j direction, the y direction, j hat. There we go. So the acceleration vector the entire time is going to be pulling up this way. So you can imagine, even though our initial velocity is in this direction, the particle will slowly begin to move outward and up toward the y direction, because that is where the acceleration is. That's besides the point. What they want us to do is they want us to find an expression for the velocity as a function of time, and then an expression for the position as a function of time, which isn't too difficult, but we do need to use some calculus. So you're going to have to rely on the fact that when you have some sort of acceleration that's given, which we do right here, if you integrate this acceleration, which we have right here, integrate, what you'll get then is velocity. So that's the first thing we're going to do. We're going to integrate this to get velocity. So there's our acceleration. We'll put that into our integral here. The 6 is a constant, so I'm going to pull it out of my integral and just put it in front here. And then my t, I'm writing it as t to the 1/2, which is the same as the square root of t. And of course, dt. And after you integrate this, you get, you're going to get 6. Stays along for the ride. T 3/2 up top here in the exponent, and then divided by 3/2 plus c. C being the constant of integration, which we're going to find in a second. Cleaning this up here, you end up getting 4 t to the 3/2 plus c. Oh, and keep in mind also, I have to keep this in mind, this is important. We had the j unit vector that was here. That's been hanging out the whole time. The j unit vector. Still here, j unit vector. Cool. Because that is what's originally with the acceleration. And it's very easy to integrate with that. It just sticks along for the ride. You can pretty much pull it out of the integral. Now we're going to use our initial conditions. If you remember, this is actually our initial velocity. Remember v naught? So you can call this v, and the argument is 0. It's basically plugging in 0 for the time, the initial. It's our initial condition. Sometimes you'll see the term here used, boundary conditions, to define this. So with using that boundary condition, we can go ahead and use our same expression here when v is equal to 0. That means you have 4 times 0, because you're putting in 0 here, to the 3/2 plus c. Now, what is v of 0 equal to? Well, we have to look back here. It's equal to 5i. So that tells us then that our c, because this goes away, c is equal to 5 I hat. All right. So our velocity expression then can be written as v of t equals, take this guy here, our 4 t to the 3/2. But now for the c, you're not going to write c. We actually have what that's equal to. Oh, and make sure you keep your unit vectors here. Very important. And put the c plus c, which is 5i plus 5i. Cool. And that is our velocity equation that actually will give us the velocity at any time t. And of course, you could put the I in front if you wanted to, but the J the term in the back. So it's in the proper order if you wanted to, but this is perfectly mathematically correct as well. All right, let's do the position now. So just like we integrated the acceleration and we got to velocity, now we're gonna take the velocity, integrate that, and that's gonna give us the position. So we can do that over here. X of t equals this integral now of v of t dt. All right. So let's see. This full thing has to be integrated. So I'm gonna break that down into two integrals here. I'll put the 4 out in front. And look, I can also take the j and put that in front. And then I have my integral of t to the 3/2. All right. And then, of course, so we have the second integral as well that we have to, and we have to close this down, of course. Don't forget about your dt, of course. And then we have the second integral. I'm going to put it down here, just to be clear. And that's that last part. Actually, it's such a short integral. We can just squeeze it right here. Plus, just a constant, plus 5i dt. Cool. And we'll go ahead and integrate those. Integrating that first part, this one right here. I'm going to be just a little bit quicker with the integration here since we did go through it in more detail here. But after you integrate this, taking care of this part first, and then you have the constant up front, and then simplifying, we get 8 over 5 t to the 5/2 and in the j direction. And then we have this guy just integrating. That's very simple. It's just 5t. The t just shows up. And that is, of course, in the I direction. And that'll give you your expression for position as a function of time. And of course, like I said earlier, if you really wanted to be professional, you could put the I component first, like so. So 5t I hat plus 8 over 5 t to the 5/2 j hat. And technically, these are vector functions, which is awesome. Cool. So we're going to box that in. That's our expression or our function of position. And we have our expression for velocity as a function of time. Position is a function of time. Velocity is a function